Hi everyone, welcome back to the channel. Have you ever wondered why you move your hands backwards when you're catching a ball? Or why stepping off a small boat makes the boat move backwards? The answer is all to do with momentum. In this tutorial, we're going to break down everything you need to know about this really important concept. We'll start with the formula for momentum and look at some step-by-step calculations with lots of examples. Then we'll look at one of the most important principles in physics, the conservation of momentum, and explain how it applies in different scenarios. Finally, we will distinguish between elastic and inelastic collisions and explain what happens to kinetic energy in each case. By the end of the video, you'll have a really good grasp of momentum and be ready to tackle any problem thrown your way. So grab your calculator and let's get started. Right, momentum is, I think, a fairly intuitive idea. You probably have done this at GCSE, and it's a nice, simple formula. So mass multiplied by velocity. So the symbol is a P or a rho, the same as density. And it's, yeah, I think a fairly intuitive idea. If you double the mass, you double the momentum. If you double the velocity, you double the momentum. So the larger the mass, the larger the velocity, the bigger the momentum. And I think there's lots of ideas of this in kind of everyday life. If you imagine a collision between a car and a lorry going at the same speed, the lorry is going to do far better than the car. That's partly because of the design and the rigidity, but it's a lot to do with the momentum. So yeah, try not to collide with a car, with a lorry. You might have seen images where cars are hit by a train, even if it's not moving that quickly, and the car is just pushed all the way down the track. So yeah, big mass, big velocity, big momentum. So the basic units are just the units of mass and the units of velocity, kilogram meters per second. We can show that the units are also Newton seconds. We might look at that later on. The key thing here is that momentum is a vector quantity. So the direction is important. And the reason why is because velocity is also a vector quantity. So velocity has a direction, therefore momentum has a direction. That's really important when we look at the calculations later on. So we need to take into account the direction of momentum. And while we're here, we can just think about the rate of change of momentum. Now, we've seen this before. This idea of rate of change is how something changes with respect to time, or the change in the quantity divided by the change in time. So we think about F equals ma, which is Newton's second law, and then we substitute the formula for acceleration into that. Then we end up with m multiplied by brackets v minus u, close brackets, divided by t. So we can expand the brackets and we end up with m times v, which is the final momentum, minus m times u, which is the initial momentum. So mv minus mu we could write as delta p, which is the change in momentum. And then we're divided by time, or the change in time. So delta P over delta T, that's the rate of change of momentum. So what we've done here is we've defined force as the rate of change of momentum. Now, some exam boards make a big thing of this. We will certainly use this formula later on. So you may be given this formula in the formula booklet, or you may have to derive it. But it's a very useful link between momentum and force. So let's have a look at some worked examples. So there'll be lots of collisions in this topic. So there'll be footballs and tennis balls and cars and a whole range of things. So this is a fairly typical one. So we've got a game of tennis, we've got tennis rackets, we know the mass, and we've got the velocity of that, and we've got a stationary ball, we know the mass of that. So to calculate the momentum of the racket, that's pretty straightforward. That's just m times v. Nice easy formula, 0.4 times by 20, we get 8 kilogram meters per second. Okay, that's the momentum. Now, importantly here, even though very often we talk about a total transfer of momentum, if you think about the game of tennis, then the racket must follow through when hitting the ball. I don't know if any of you play tennis, but if you try to stop the racket when it hit the ball, that would be almost impossible to do and would result in a really bad shot. So the racket continues to move after contact. So we only transfer some of the momentum. So we've here estimated 25%. So we can just calculate 25% of 8, which is 2, so that's fine. So we've transferred 2 kilogram meters per second of momentum to the tennis ball, and now we're trying to find the velocity of the ball. So we know the momentum of the tennis ball is 2, so m times v is equal to 2. If I know the mass is 0.05, I can divide by the mass of the tennis ball and work out the velocity. So this is one of the reasons why the tennis ball moves so quickly, is because it has a low mass. So if we give it some momentum, then it's going to have a large velocity. So that's quite a key idea there. We could talk about kinetic energy as well. So it's a nice simple calculation. We'll talk about this later on when we look at elastic and inelastic collisions. But if I calculate half mv squared before the collision, so this is of the racket, I've got 80 joules, and half mv squared of the ball after collision, that gives me 40 joules. So, well, 80 to 40, that's half, 50% of the kinetic energy is transferred. So that's an important thing to realize, that when we have collisions, we could talk about momentum and transfer of momentum. We could also talk about transfer of kinetic energy. And we'll talk about elastic and inelastic collisions later on. Another worked example. So here we've got a ball traveling at a certain velocity. It hits the wall and bounces back along the same path. Now, this is a really important idea where we have to consider the direction of momentum. This is a very, very typical question. So we can find the change in velocity of the ball. Well, a common mistake here is if I have 15 meters per second in that direction and it bounces back traveling at 10 meters per second, a very common mistake is to just do 15 minus 10 and get 5 meters per second. But that's obviously incorrect, because it has not taken into account the direction of velocity. So delta v, the change in velocity, is v minus u. So if I say that v, the final velocity, is 10, which is positive to the left after collision, then I subtract the u, which is 15, but that's in the other direction. That's minus 15. So I add these two together. Minus and a minus become a plus. So that's really important. You could define a positive towards the right, in which case you get minus 25, which is absolutely fine. So then we work out the change in momentum. So it's just the change in velocity multiplied by the mass. That's straightforward. It's 1.25 kilogram meters per second. So that's a really important idea, the idea of momentum is a vector because velocity is a vector. So you have to take into account the direction. So here it says find the average force exerted by the wall on the ball. Okay, again, positive, I'm going to assume to the right, I think, but we could easily assume to the left. It doesn't really matter. But in this case, if we've got a time, then we're going to have to use this formula that we derived previously. So we're defining force as the rate of change in momentum, m times a. A is v minus u over t. And we've already worked out mv minus u. We've already got the change in momentum. So all we need to do is just divide that by the time. Watch out for the milli, which is 10 to the minus 3, and we get 52.1. So we could say, well, is that to the right or to the left? Well, if it's the force exerted by the wall on the ball, this is the wall pushing the ball to the left. So the 52.1 newtons is definitely acting towards the left to change the direction of the ball. Whether that's positive or negative is entirely up to you, depending on your frame of reference. But importantly, we could talk about Newton's third law here. So if there's a force of the wall on the ball to the left of 52.1 newtons, there must be an equal and opposite force of the ball on the wall to the right of the same value. Now, if you want more examples of these, if you go to payhip.com, grade A physics, then there's a whole unit on this if you want to work through that. Worked examples, exam questions, and some review quizzes as well. Right, let's have a think about conservation of momentum. Now, you may have seen this demonstration if you by your physics teacher. So an air track is a lovely bit of kit. So you have this long piece of metal, and air is blown up through these little holes to lift these gliders off the track by a millimeter or two. So it doesn't totally remove the friction, but it does reduce the friction quite a lot. Obviously, it doesn't change air resistance. But what you would find, if you have one collider colliding with the other one and then stopping, then you should notice that the second collider moves off with the same velocity if these two have the same mass. And if I double or increase the mass of the first one, then that collides with the second one. If it has twice the mass and it transfers all of its momentum, then the second glider will move with twice the velocity. And you might also see a demonstration where you put the two together, maybe with repelling magnets or with elastic bands, and then you release them. And they should, if they have the same mass, have the same velocity in either direction. So that's a lovely illustration of conservation of momentum. So the law of conservation of momentum is this: within a closed system, which means there's no external forces, we're only considering the forces acting between object A and object B, the total momentum in any direction is constant. So the law of conservation of momentum does what it says on the tin, basically. Momentum is conserved, but you must have this condition here, so that they will insist in the exam that you write that. And there's lots of examples of this. So one example might be firing a gun. So some of you may have done this, possibly with a shotgun, as a recreational pursuit, hopefully. So before you pull the trigger, the momentum is zero. There's no momentum backwards or forwards. And then this literally is an explosion. It's a chemical reaction, and the bullet or projectile will be fired out the end of the rifle, and then there will be a recoil. So if any of you have experienced this, the guidance is you need to hold on to the rifle or the shotgun really, really tight, hold it into your chest and lean into it, because you're going to get a kickback. You're going to get the recoil. And very often films and movies show this in a very bad way, that they don't show this as an issue. So the recoil is an example of conservation of momentum. So we can look at this in an algebraic way. If I have M1 and M2 before a collision, U1 and U2, and then the same masses after a collision, V1 and V2, then I can represent the total momentum before as M1 U1 plus M2 U2, total momentum before, there we go, is equal to the total momentum afterwards. So the M1 and the M2 haven't changed, but now the velocities have changed. So we're now talking about the final velocity V1 and the V2. Now you don't have to write this out, but if that makes sense to you, it's quite a nice algebraic summary of conservation of momentum, and it's a good thing to write out in any calculation you do. Alternatively, you could write out the statement of law of conservation of momentum, but it's a good idea when answering a question to write that out, and even if you get the answer wrong, hopefully you'll get a mark at least for writing that statement. So let's look at some examples. So this is a straightforward one. This is more of a GCSE question. I've got a mass traveling at 10 meters per second, and it collides with a slower moving mass, 6 kilograms, moving at 4 meters per second, and they stick together. Now, if these were rolling balls, then they probably wouldn't stick together, but ignoring that slight issue, so they collide and they stick together. This is probably more applicable to vehicles colliding, probably, in which case they stick together. So total momentum before we can work out is m times v, 5 times 10, plus m times v, 6 times 4, and we could work that out if we wanted to. But then I could write this as an algebraic expression, because the total momentum before is equal to the total momentum afterwards. Now the reason this is more straightforward is because these two are stuck together or locked together. So now the total mass is 5 plus 6, which is 11, and we can work this out and find the combined velocity. Now you might get one that easy at A level, but this is more of a GCSE question. So more likely you'll get something like this, where you have the objects are moving in opposite directions, and then afterwards they bounce apart, so they don't stick together. But we can approach this in the same way, but we have to be careful of direction. So I would assume to the right is positive. You don't have to, but if I do that, then the 8 will be minus 8, v will be positive, and the 2 will be positive. So once again, 4 times 5 to the right, plus minus 8 times 6, because that's moving to the left, negative 8. We could work that out. That's the total before. Is equal to the total afterwards. I've got 5 times v plus 6 times 2. Now you might be thinking at this stage, intuitively, you'd expect the 5 kilogram to bounce or move to the left after the collision. And actually, you would be right in assuming that, because it comes out as negative 8. So if we've assumed to the right is positive and v is positive, if it comes out as minus 8, it actually means it's moving to the left. which is probably what you would expect. So you might be asked to calculate the magnitude and state the direction. Again, if you want more examples of this, go to payhip.com grade A physics. Final thing we need to consider is the types of collision. So an elastic collision is when kinetic energy is conserved. Now it's really important to include the word kinetic. If you say that energy is conserved, well that's always true. That's the law of conservation of energy. So that's not particularly helpful. And if you miss that out in the exam, you won't get the mark. So an inelastic collision is where kinetic energy, again important, is not conserved. It's converted into other forms of energy, usually heat and maybe a sound or light or something like that. So we've actually got a whole scale here between two extremes. We have perfectly elastic up on this end here. Now that's quite difficult to find any situations like that. The closest we can get is it's an atomic or subatomic situation where there is no friction, maybe two protons repelling. That might be an example. And at the other extreme, we've got perfectly inelastic. And again, it's quite difficult to find an example where all the kinetic energy at the start is dissipated into heat. So you might get a situation if you have two cars crashing head on, that might be considered perfectly inelastic or very close to that. But most collisions in everyday life are somewhere between these two extremes, and we call those inelastic rather than perfectly elastic. So maybe in sports, or the little office toy with the Newton's cradles and the ball bearings. So that there might be a range of values here. But importantly, even though collisions can be elastic or inelastic, momentum is always conserved. And that's a really, really important point. Okay, we could do a worked example, and you might be asked to do this in the exam. So you might be asked to calculate the momentum, or maybe show that momentum is conserved. So m times v plus m times v, m times v plus m times v. In this case, momentum is conserved. That's what we would expect. If it was not conserved, then there's something maybe wrong with the data or something else going on, or maybe there's other forces or other things happening. If I was to work out the kinetic energy before and afterwards, there's no shortcuts here. Some students try to work out the average velocity and add the masses together. That's not going to work because it's half mv squared. So we have to calculate half mv squared plus half mv squared. We get 5,300. Then afterwards, again, half mv squared plus half mv squared. In this case, we get 5,300. Now, that's very unusual. If this is a real world situation, that would not happen. So maybe in the exam, you'd be asked to comment on that and say this is unusual. Normally, we would expect this to be inelastic because some of that kinetic energy will be converted into heat. Great, okay, so we've covered a lot in this video. So if you want to see the next video, that will be probably Physics A-Level Vectors. That should be on YouTube. If you want more detail, more content, more practice questions, exam tips, exam questions, progress tracking, and quizzes to check your understanding, go to payhip.com, grade A Physics, and see you soon. Bye.